We continue our study with exponents. Last time we talked about all of the mad spam rules, which is when we're multiplying bases, we add the exponents. When we divide the bases, we subtract the exponents. When we have a power raised to another power, we multiply those powers together. Here are the rules in words and exactly off of the formula chart, as well as some examples that we did last class. We're going to continue on our study of exponents with some other exponent rules. These don't have funky titles, so unfortunately they're not all grouped together the way mad spam is, but they're really pretty easy. The negative exponent property I like to call hammer time, because the guy who's saying hammer time was named MC Hammer. Now MC Hammer helps me remember that I'm going to have to move and change these exponents. The rule for a negative exponent property is that if you have a negative exponent, you're not allowed to leave that as a final answer. So when I get a negative exponent, I need to move and change it. Move means I'm going to move it to the bottom of a fraction bar, and I'm going to change that power to be positive. Now, since I can't have just a blank numerator, I'm going to put the placeholder of 1. This really is just changing the term, the base and its power, to the opposite side of a fraction bar, and changing the power to positive. That's literally the entire rule. So this x to the negative 2 power, I'm going to actually change, move it, change it, and then put that placeholder. X to the negative 2 power is equal to 1 over x squared. And even though it might look more complicated, I'm doing air quotes, you can't see me say the word complicated, is actually simplified when we don't have negative exponents. Now what's important is that you never change the bases when you're doing this, okay? We don't want to change that negative 2 when we have negative 2 raised to the negative 5 power. We will take the entire negative 2 and move it to the bottom without changing the base. Whatever the base is stays exactly the same. The only thing we do is move it. We change the exponents. That's it. That's the whole rule. That's hammer time. MC Hammer. Move and change. If we look at the challenging examples, the only reason that these are challenging is because they have multiple pieces. Now, only the parts that are negative need to move. So this x squared that's in the numerator right now already is positive. So I don't need that. I need to move the y to the negative 3 power because I'm not allowed to have negative exponents anymore. Since it's in the denominator, when I move it, I'm going to move it up here to the numerator. Move and change. Now that denominator has nothing in it, so it's a denominator of 1, but I don't need to leave over 1s, okay? 5 over 1 is the same as 5, so x squared y cubed is the same, or over 1 is the same as x squared y cubed, okay? Now this last one, the current exponent of 2 is 1. The current exponent of z is negative 5, and the current exponent of x is negative 2. There are only 2 parts that need to move. The 2 does not need to move because it's already a positive. It's going to stay in my numerator. But the z to the negative 5, I'm going to use the hammer time rule. Move and change. Same with the x to the negative 2, I move and change. And that is the simplified version using that negative exponent rule called hammer time. The second property that we're going to be talking about today is called the zero exponent property. Y'all, this exponent property is so easy they didn't even put it on your formula chart. So all of your mad spam and your hammer time rules are on your formula chart, but the zero exponent property is so easy they didn't put it there. The zero exponent property is when any base is raised to the power of 0, that's equal to 1. That's it. That's literally the whole thing. And it can't really get any more complicated than that. So if I look at these examples I have, if I have 4 raised to the 0 power, you should automatically say, well, that's 1. A good old-fashioned number 1, not anything to the 1 power, just literally a straight-up 1. Doesn't matter how complicated the number is, like 98,347,529,354 to the 0 power, well, that's equal to 1. Don't overthink it. Anything, no matter how complicated it is, raised to the 0 power is 1. To try to make this more complicated, what you might see is the 0 power worked into a separate problem. So like this first one says 1 plus negative 30 raised to the 0 power. Well, negative 30 to the 0 power is equal to 1. So 1 plus 1 is actually 2. We use the property within a different problem. In the second one, even though this piece right here looks super complicated, it is raised to the 0 power, which means it's 1. 1 minus 25 is equal to negative 24. And that's it. The last exponent rule isn't technically an exponent rule, in all honesty. But what we're going to need to be able to do is do all the operations that we can with exponents. We talked about multiplying. We talked about dividing. We talked about exponents. We've talked about negative exponents, but we haven't talked about adding and subtracting. Adding and subtracting monomials is actually something we've been doing for a while, and all that we need to do here is combine our like terms. Now we're going to be picky for a while, and when we do combining like terms when we're dealing with exponents, we need to make sure we write these in standard form, which means we're writing it in decreasing exponent order. Decreasing means going down. So what I mean by that is when we get our final answers, we need to make sure that the expression starts with the largest exponent going down to the smallest exponent. This is especially going to help you in Algebra 2 when you get to really long polynomials. Now, adding and subtracting. We don't use any of our exponent rules. This is just combining like terms. We find terms that are like, which means the base and the power are the same for the whole thing. 9x squared and negative 3x squared are alike, but they are not the same with 9x because 9x is not squared. That means when I simplify this, when I combine like terms, I'm just going to add together 9 and negative 2 and get 6x squared and let the 9x follow down. This is in decreasing exponent order because the biggest exponent is 2. The next exponent is 1. That's decreasing, so I'm good with my order. The second example, we have 2x squared, and the only thing that it's like is negative 5x squared. Some people might ask if it's like with 7x cubed. Well, no, because this is x to the third power. That's not the same term as x squareds. So I would combine the x squareds, 2 plus a negative 5, that's negative 3x squareds. There's nothing that's like with the 1, and then I have the 7x cubed that has nothing to combine with. This is not in decreasing exponent order, however. We need to make sure that the biggest exponent goes first. So I'm going to take the 7x cubed term, write it first, then the next smallest exponent, followed by the constant, which has an exponent of 0, because this is really like 1 times x to the 0 power, which is 1. Okay, the only way we can make these sort of rules more complicated is if we start to cram in a lot of exponents and variables into the terms. For example, we have 9x squared y and negative 10x squared y and 2xy. These three things are not like terms because even though they all have x's and y's, this term does not have an x squared. I can only combine like terms, which means this would combine 9 minus 10 is negative 1x squared y's, and then the 2xy gets to float down. And that's the simplified version. Again, I don't change the bases or the exponents at all. I'm only changing their coefficients. Same thing like we've been doing for combining like terms for forever. Now there's two options we could do for this one. Sometimes people will read this and think this is 6w minus 8w, and others might read it and say 8w minus 6w. Well, if I read this and I say I need to subtract 6w from 8w, it's kind of like saying I want to take away 6w from 8w. The one that represents this correctly is the second one. And again, though this doesn't look like an exponent problem, technically these are matching exponents. So I can combine my like terms to get 2w or 2w to the first power. That finishes up all of our exponent rules. So we started off with mad spam, multiply, add, divide, subtract, power to a power, multiply the exponents. We got our hammer time rule, which means we got to get rid of our negative exponents by moving and changing MC hammer. We have our zero exponent property. Anything to the 0 power is equal to 1, no matter how crazy it is. And then when we want to add and subtract these terms with exponents, we have to make sure we're combining like terms. Otherwise, we cannot combine them. We'll have polynomials, which means many parts, when we finish problems like this.